And in this data file, I included the problem 6.11 and 6.13. 6.11 is the R&D project selection problem. 6.13, which is the unit, the fixed charge problem. We're going to do it here together, and I'll guide you through it. So copy those data to a new sheet. Okay. And then let's go back to see. We have two sets of decision variables. The first ones being the amount of product I to be produced. Okay, so here we will have some space reserved for the decision variables. Okay, so will be number to produce. Okay, and these represent our xi's. Okay, and then here for the yi's, because for each x we have a y, so it's natural that we'll just put yi's here. So, and these yi's represent whether we'll have a setup cost or not. Okay, so we'll have say setup cost, will it happen or not? And we know that if it's 1, yes, otherwise 0. Okay, so xi's and yi's. Then, so this with this we reserve the space for our 6 decision variables. Okay, next we'll look at the objective function. We're going to maximize the profits, subtract the setup cost. Okay, and both parts represent some product of the units, the coefficients, and your decision variables. Okay, so here we'll say we want to maximize the total profit. And the total profit was calculated by using sum product of the unit profits with the xi's representing the first section. Okay, this section part. And then subtract sum product of the setup cost and the binary variables that will turn them on or off depending on whether they need to be included in this objective function. Okay, so this is the objective function. Okay, and I'll highlight it in blue. So now we took care of the decision variables and objective function. Okay, next we'll look at the constraints. First group of constraints, very easy. You can do it by yourself. Okay, would be the resources needed for the 3 types of resources to produce 3 types of products, less than equal to the available resources for each type. So in the given data, we have the resources, unit resource needed. We also have the total resource available. So I'm going to insert a column here to calculate the total hours needed. Okay, and I'll clear the shading here. Okay, so the total hours needed will be sum product of the unit resource requirements and our xi's. Okay, and later I want to copy this formula down, and I don't want this row to shift, so I'm going to put the $sign before the row number here. Okay, so that's the resource needed for machining. Okay, and I'll copy this all the way down here. Click inside the last one to check. Okay, so that's the resources needed, and I'm going to shade them in red. Okay, so that's the first group of constraints. Okay, then the second group of constraints we'll look at are the linking constraints that represent the relationship between the x and y's. Okay, and they represent this relationship here. And last time we talked about that when xi is greater than 0, y have to be equals to be 1. And this relationship is reinforced by these constraints. Okay, and these constraints do not really reinforce the second part of that constraint, which is when xi equals to be 0, y need to be 0. Okay, but this relationship, we don't need to have a constraint for that, because if we look at the objective function, when the y's do not have any constraint to force their value to be 1, they will be 0 for sure, because of the objective function is trying to maximize this amount, subtract those really big values as a coefficient of your y's. So if we don't have any constraints to force y to be 1, they will be 0. Okay, so and with this constraint we have, we will be able to enforce that y to be 1 when their corresponding xi are greater than 0. Now, where did those 50, 67, and 75 value come from? They are not given anywhere, right? Do you guys remember where did we calculate them? Okay, to answer this question, first you need to think about what are those values represent. Okay, those values represent the upper limit of your xi's. Okay, because remember when we tried to come up with those constraints, what we had first is x1 less than equal to y1, to force that when x1 is greater than 0, y1 need to be equal to be 1. But we said that x1 is not a binary variable. It can go from 0 to a big value. And suppose that's m1. Okay, it can go from 0 to m1. And we don't want this right hand side to limit, to restrain that x1 to increase. Okay, so we come up, okay, let's just multiply a value here so that x1 can go all the way from 0 to m1. And we find out this m1 value by calculating the maximum value that x1 can be. Okay, so, and we did that by calculating, assuming for x1's upper limit, we assume that x2 and x3 being 0, and we use the right hand side divided by the coefficient of x1 in these three constraints and find the minimum value among them, which is 50. And we concluded that 50 is the maximum value that x1 can be. Okay, so we're going to use the same thing, same relationship, even the same formula to calculate this upper limit for x1. And we're going to use it somewhere here, so I'm just going to move this formula down 2 rows. Okay, here I'm going to calculate the upper limit of xi, which is the mi. Okay, we use m to represent a big value, so we call it the big M. Okay, so this big M for x1 equals to be the minimum among this right hand side divided by x1's coefficient. Okay, and this right hand side divided by this coefficient here, and this right hand side divided by the coefficient here. So that's the minimum value of these 3 divisions here. Okay, and I want to fix the numerator column. Well, I copy this formula to this column and this column. I do want these coefficients, denominators to change, but I don't want these numerator change. So I'm going to put a $sign before the column number of the numerators. Okay, and then copy it all the way. Click. Okay, and the other way to check is, you see that we did get the same value as what we calculated in class. Okay, so it's a 50, 67, and 75 here. So we do get those values here. Okay, so these are the upper limit, the big M for our xi. And to get the left-hand side of the constraints, we'll need the xi subtract the big M times the y. Okay, so here in this row, I'll just put it's the xi subtract mi times our yi. And we'll just make sure like this row is less than or equal to 0 when we go to set up the solver window. Okay, so here, this one, this equals to be our xi subtract the big M times the y. Okay, so x subtract the product of these two. And then copy it all the way here. Okay, and then highlight this row to be a constraint, the left hand side of our constraint. Okay, now we took care of these constraints, and what will be left will be the xi's being integers, yi's be binaries. Okay, and xi's greater than 0, and that need to be defined in solver. Okay, so let's go to the solver. Objective is the total profit, and we want to maximize it. Okay, and the variables, we need to add both rows, the xi's and the yi's, to be the variables. Constraints. Okay, first group of constraints will be resource needed less than or equal to resource available. Okay, add the xi minus the mi times yi need to be less than or equal to 0. Okay, so 0 is the only time that we put a value in the constraint table. Otherwise, we always use a cell to contain this numerical value and refer to that cell in this solver window here. Okay, and we need to add that our xi's need to be integers because we want our product number to be integers. And we also need our yi's to be binaries. Restrict that they can only be 0 or 1. Now, okay, and we want to make our xi's to be non-negative. Okay, and change the algorithm and solve. Okay, solver find a solution. All constraints and optimality conditions are satisfied. Okay, I don't know if you guys still remember, we did talk about the message last time. Okay, I got this message that's because that in this option here, the integer optimality tolerance I set to be 0, which means that solver needs to find the best optimal solution for me. Okay, but we also talk about that because the algorithm used to solve integer linear programming takes a long time. Okay, it's different from the LP algorithm. It need to go through sometimes millions of sub-problems depending on how big that feasible region is of this problem. Okay, and so sometimes it could take a long time, and if we say, okay, we are satisfied if the optimal solution, the objective function value is within, say, 95% of the object function value found without those integer constraints, then we set optimality percentage here like this. Okay, note that when you solve your problems in this class, change your option value from the default. I think default is 0.05, 1.5% deviation to 0%. Okay, so you get the optimal solution. That would be the same for everyone. Okay, and let me just change this again. So if we have say 0.05 here and solve again, you see that the solver message will change. Solver find the integer solution within tolerance, and this tolerance is that 5% deviation that we talk about. Okay, since in the previous solution, the optimal has already been found, so it still give me this one, even when I changed that tolerance value. But the solver window, the message is changed. Okay, so I'm going to go back, change my tolerance back to 0. Let's look at the solution given. Okay, so you can see that in the optimal solution, it is suggested that product 2 and product 3 should be produced. Product 2 need to be produced at 55 units and product 3 32 units. And you see that the setup cost for products 2 and 3 did occur. Okay, and it's represented by the Y value being 1 here. Okay, and if you look at product 1, it is not suggested to be produced 0 units, and the setup cost did not happen. Okay, and if you look at the given data, it makes sense. Okay, see, the unit profit of product 1 is 48, less than the other two, but the setup cost $1,000 is more than the other two products. Okay, and if you look at resource consumption of these three, product 1, it consumes 13 units, and this one consumes 12 units, this one consumes 12 units. So product 1 is really not economical to be produced. Consumes the most resource, have the highest setup cost, and the lowest unit profit. Okay, so it's not suggested to be produced in this optimal solution, which makes sense. Okay, and so this is one way to check whether your optimal solution makes sense. And I hope that you develop the habit to take a look at the solution to see if it makes sense to you after you solve every problem. Because one disadvantage of using solver is that sometimes it may find a solution for you, and especially if you don't read that solver window carefully, it will find a solution and there will be some value appearing here, and don't just take it for granted. Okay, take a look and using your common sense, your heuristic, to see whether the solution makes sense to you. Okay, so this is the Excel model that we created for problem 6.13, the fixed charge problem. Please finish your Excel spreadsheet and keep it, because next week we're going to continue use this spreadsheet as the following problem build onto this one. Okay, so it's important you complete it and you keep it for use next time.